Okay, so if you go to Compass and you go to course content and scroll down, well, first of all, there's MSE490_software.x. So if you want to install lamps, there are instructions in there, as well as on the website. So take a look in there first. Okay, and so if we go down to lamps, there are some slides. So that was the principles, that was the practice that we just looked at. And then if you go to walkthrough, here are a bunch of input files, some MATLAB scripts we're going to use, and here's the actual walkthrough itself. So if you go ahead and download all of those, basically, so if you pull down the input files, which end in .in, and you pull down the MATLAB scripts, which end in .m, and also pull down the slides. So if we go ahead and do that right now. So Mohammed, I will email you this right now. Okay, has everyone got those? Okay. Okay, great. So let's start taking a look at those guys. Okay, so this is now the walkthrough component. So we're getting a little ahead of ourselves, so we were planning to start this next week, but we got plenty of time today, so let's get cracking on this right now. Okay, so walk through lamps and Ovito. So the software we're going to use, like we said, is lamps, and the visualization package we're going to use is Ovito. And so the EWS pre-installation is available in a similarly horribly long path to where we found the Quantum Espresso executable. And so what file can we change in order to save ourselves having to type this whole thing? Bash RC. So let's do that together now. So let's pull up a terminal. Okay, so I'm logging into EWS. You guys are already on the EWS, you don't need to do that. Okay, so if you go to your home directory, .bash rc, so you're going to edit this file, .bash rc. It turns out my system is different than yours for some reason, so I have to edit bash profile. And then you want to type a line. You should have something like this line when we were doing Quantum Espresso. And so you want to add lines very similar to that will look something like this. I'm sorry? Oh yeah, absolutely. Yep. And so a nice way to not have to type that whole thing and look at the screen is actually to, so I'm going to exit out of this file, is to from my terminal go to that location, so class MSE 498 AF, it's going to be software, it's going to be 3 labs, and it's going to be lab fab, SRC, and there should be, yeah. And so I would just navigate there, and then I would just copy this whole thing. Then you can copy and then paste that into your bash RC file. So what I did was actually get the terminal to navigate to the place that I want, and so I know for sure that I'm not going to make any typos because I'm just going to copy this whole thing, and then I'm going to dump it in my bash RC. Or, of course, you can just type it. Okay, so let me come around and see if anyone's having problems with it. Hi.
Are these programs independent of each other? Because when I opened it, it was already here.
So you must have added it at some point.
Because I didn't.
Okay.
Does that mean that somebody else installed on this computer? So next time I log on to somewhere else, it's not there?
No, this is your own space. So this is your profile.
I didn't do that.
Okay.
Okay, well, it's here. So.
All right, well, good. Yeah, I guess if someone has your login details, they're doing nice things rather than doing horrible things. Yeah. I'm sorry, say that again? Right. So EAM tends to be a little faster than MEME because there are less sort of parameters in the force field. So if you want to simulate a metal, typically you're going to have to use a potential that's like EAM or MEME, and so you just have to use it. It's inefficient in the sense it's not pairwise decomposable, and so it's actually got multi-body terms in it, which makes it a little slower, but you can still parallelize with it. Right. Oh, okay, so this, I don't mean it to weak and this is bad. Okay. So what I was saying is there's two ways of evaluating scaling. There's so-called strong scaling, which as you throw more and more processors at a problem, how big a speed up do you get? And then there's weak scaling, which it says I'm going to keep the size of the problem per processor fixed and see how the scaling goes as I add processors. So I might do 32,000 atoms on one processor, then I would do 64,000 atoms on two processors, and that's what this is showing. So it's saying that even though no, so weak scaling is a technical term. I don't mean that it scales badly. Yeah. Okay. Is anyone else having difficulty with their bash RC? Does anyone still need a little more time? Okay, great. So that means that you no longer have to type that big horrible thing. And so if you close your terminal, because we remember that the bash RC file is only picked up once you boot a new terminal. So you close the terminal, reopen one. If you type LMP _G and then press tab, you should get something like this. So remembering that tab does the autocomplete. And then if you press enter, you will get something that says labs, and then it will do nothing because it's waiting on input. So has everybody got that? Has anybody not got that? Okay, congratulations. That was much less painful than when we first modified our bash RC file, so you should all feel very proud of yourselves. You're not experts in doing that, so great. Okay. So I'm just going to quit out of that. So log out. Terrific. Okay, and so now when you type LMP _G++, you should get lamps, and actually you can test, if you also type Ovito and hit enter, you should get Ovito to boot. We're not going to use that immediately, but you'll see a nice GUI will come up on your screen if you just type Ovito. Ovito. All lowercase, O-V-I-T-O, and then hit enter. You should get a nice. Everybody's got that? Anybody not got that? Okay. Okay, so probably there's some error in your bash RC. So let's take a look at your bash RC. Oh, so that was still running lamp. So try typing it now.
Oh, okay, okay. I just think
okay, so let's take a look at your bash RC file. Okay, so you need to add the line for Ovito also.
Oh, okay.
Which is, you go down a little bit.
Okay.
That guy, yeah. Yeah.
Can I type Ovito?
You should just type Ovito, and it should launch.
That.
Yep.
Okay.
Looks good.
How do you know that from the?
So that's just the locations in which I installed them.
Okay, so that's.
So I pre-installed, and I chose to put it there. That's right. Yeah. So when you install at home, you can put wherever you like. Yeah. Anyone else have any Ovito problems? Yep. Yeah, mine has done that when I log in remotely. It seems to be some of these workstations do not have OpenGL properly installed. Interesting. Okay. All right. So let's put a pin in it and see if it repairs itself. Okay. Okay, everybody good? Anyone need a little more time? Great. Okay, so let's proceed. Okay, so we're actually going to do two little walkthroughs, sort of back to back. The first one's going to be super simple, and it's not actually going to be molecular dynamics. The second one is actually going to be molecular dynamics. And so let's see what we're going to do the first one. So the first one, we're going to use lamps to estimate the aluminum FCC cohesive energy. And so the thread through all this course is basically aluminum. And so you studied aluminum in your project for Quantum Espresso. We're going to study aluminum in this walkthrough. We're going to study aluminum again when we do finite element modeling, and we're going to study aluminum again when we do calculation of phase diagrams. And so it's all about aluminum. So the thing we would like to compute is what is the cohesive energy of aluminum and what is the lattice parameter. So the lattice parameter is something you computed in your project using DFT. Now we're going to compute it using a classical force field in molecular dynamics, and we're going to see how good we did. Okay, so we all understand the lattice parameter. It's basically how far apart are the atoms in your crystal. What is the cohesive energy? The cohesive energy is a super simple concept. We measure the energy of aluminum when it's in its solid phase with its equilibrium lattice spacing. And then we measure the energy of aluminum when all the atoms are separated to infinity. And so we take aluminum and we just nuke it and blow it up, and all of its atoms go out to infinity, and we measure that energy. And so this is exactly zero, because when all the atoms of your aluminum metal are separated infinitely, they don't interact, and so their interaction energy is zero. So basically, if we can measure the energy of the solid, then we have the cohesive energy. And so the cohesive energy is an important quantity in material science because it basically tells you how tightly bound your atoms are in your crystal. So things with very high cohesive energies tend to be bound very tightly. Things with low cohesive energies are bound more weakly. So maybe it's an interesting thing we would like to calculate. Okay, so experimentally, the cohesive energy is about 3.39 electrovolts per atom. And the equilibrium lattice constant, which is something you've probably found in your project, is somewhere around 4 angstroms. So what are we going to do? And so what I'm trying to illustrate with this walkthrough is, first of all, something that's sort of analogous to what we did in Quantum Espresso, but now using a completely different physics, using classical mechanics. And we're going to do something relatively simple because the input file is sort of complicated, and so I want to give you as simple as possible an input file, and then we can build on top of that in the next walkthrough. And so we're going to use an IM potential for aluminum that we're going to download from NIST, and we're going to use that to try and optimize the cohesive energy as a function of A, which is to say we're going to try and find the equilibrium lattice spacing that gives you the lowest cohesive energy. So similar to when we were relaxing things in Quantum Espresso, we were changing the value of the A lat in our fundamental simulation cell until we got the lowest energy. We're doing exactly the same thing here. So just to be absolutely crystal clear, this is not molecular dynamics because we are not integrating equations of motion. We're just changing the lattice parameter and we're evaluating the in potential to figure out what the cohesive energy is. So it's very similar to quantum espresso when we were actually not doing sort of DFT calculations. We were basically just doing a relaxation. Each stage we would change the lattice spacing, we would evaluate the energy, we would change the lattice spacing, we would evaluate the energy. Very similar here. So all we're doing is we're using lamps as a tool. We're giving it a configuration file with a particular lattice spacing. We're giving it a potential, the E potential, and we're saying, hey lamps, what's the energy of our system? We're not computing forces, we're not computing particle updates, we're going to do that later. Is that clear to everybody? Okay. So basically we're doing a potential energy minimization. And we're going to achieve this by doing gradient descent, very similar to what we did in quantum espresso. So there's not going to be any atom velocities, there's not going to be any temperature, there's not going to be any pressure, stuff like that. That's going to come later. So let's do something very simple first, then let's do some molecular dynamics. Okay, so your first job is to get a potential. So I provided you the link here, and so if you navigate to this website, it's basically the NIST website where they store all the potentials. You'll see a very nice periodic table, and you can start clicking on elements, and so the element we're interested in is obviously aluminum, and you'll see a big list of potentials. And so then you can select particular potentials to download. They all, I think, are basically eames or means. There may be some other fancier ones in there. The one that you're interested in is al99.eam.alloy. And so once you've clicked on aluminum, maybe you just want to use the find command, so Control F, type in al99.eam.alloy, and it will find you the right potential. So just be a little bit careful because there's a lot of potentials that are named very similarly, so make sure you do get the right one. So this is now a great resource. So you now know where to find potentials for whatever system you might be interested in. So there are elements, there are a smaller subset of compounds, and then sort of binaries, and there are a smaller subset of sort of ternaries. You can grab them all from NIST. And so a very nice place to find the potential for the system you care about. Okay, anyone need a little more time to grab the file? Great, okay. So now what you should have are the three things that we need to run a simulation. So like we said, you need an input file. The one we're going to look at is al_scc.in, which you pulled down from Compass. You now have a potential, al99.eam.alloy, and you have the executable. And so the executable we have is lmp_g++3. And so these are all the ingredients we need to make LAMPS run a simulation for us. So like always, actually running the simulation is trivially easy. You could type the command into the terminal, it would run, but you'd have no idea what you did and no idea what you calculated. So obviously we have to sort of get a handle on what we're doing and understand what LAMPS is going to produce. So what we're going to start today is looking through the input file. And so open up any text editor, al_scc.in, or you can open it directly in the terminal using left or head or whatever you like. And we're just going to run through this input file and spend a good amount of time understanding what all the inputs are, and that will then give you the tools to actually write your own input file. And so you can modify this and make it for any system you like. So what I'm hoping here is that as we run through the different chunks of the input file, you'll be able to use your new knowledge about molecular dynamics simulation that we covered in the last two lectures to understand what parameters we're inputting and why. So that's the idea of giving you the fundamental grounding in MD theory, because now you have the ability to understand and eventually write your own input files for a LAMP. Again, if I just shown you this on day one, it would have made no sense to you, and that wouldn't sort of been a very useful thing for you to learn. Okay, and so let's look at the top line. And so if you start a line with a hash that is means it's a comment, and so it's always good practice when you're writing input files to comment stuff. It's good for you because if you come back and look at this in 6 months, it leaves you a sort of trail of lentils to understand what you did. And it's good if you want to share your input file with other people so that it's not completely impenetrable to them. So comments are great. Use comments liberally. Okay, so we're starting the comment line, and we're saying we're initializing the simulation. And so we first have to tell LAMMPS what units we want it to run in. And so it turns out if you're using the potential that we downloaded, al99.im.alloy, you want to be using units metal. And so LAMMPS can operate in SI, it can operate in English units, it can operate in what's called metal units, CGS units, and you can look up the manual and see exactly what all those unit systems are. And so if you look up the manual and you figure out what the metal units are, it tells you here all of the different units. So mass is measured in grams per mole, time is in picoseconds, distances are in angstroms, and so these are the units that the IM potential is expecting. So we've got to make sure we have consistency there. And I think if you go to the NIST website where you downloaded this, it will tell you that it was written in units metal. Or if you actually open up this file in a text editor, it will tell you it's in units metal. So very important that we have consistency there, or our answers are going to be garbage. So again, garbage in, garbage out. Okay, so think about this as a reference place. And so once you compute stuff in LAMMPS and it tells you what the pressure is, you can come back to this slide and say, okay, pressure's in bar because I'm using units metal. Okay, so dimension 3, typically you want to simulate 3-dimensional systems. Makes sense. You can also simulate in 2 and maybe even 1 dimension, if that's interesting to you. Boundary PPP. Sorry, question.
Can it handle higher dimensions from a mathematical standpoint?
I don't know. That's a good question, actually. You could try it, see what happens. So there's no reason why the math will not work in higher dimensions, but probably it's not equipped to do that. Yeah. Yeah, so when I went to grad school, there was a chap in the chemistry department who was, Salter Quasso, who was interested in sort of packing spheres in n dimensions. And he wrote like an n-dimensional molecular dynamics hard sphere code to like pack spheres. So it was really cool. I guess they're very interesting mathematical questions. But yes, it's super abstract, but in principle, the algorithms will run in an n-dimensional space. Okay, so boundary conditions, we want to be periodic, so it's PPP. We're periodic in X, periodic in Y, periodic in Z. And so that was that trick because we want to simulate a bulk system. And so we have periodic boundary conditions in all directions. And then we say atom style atomic. And so it just turns out the way that LAMMPS can specify the atoms in your simulation. There are a number of ways of doing that. The most common way is using sort of the atomic style. You can look up the manual and see what other styles there are. So basically it tells it that it should expect sort of a name, a mass, a charge, and some coordinates. Using other styles, you can supplement that with extra information that may be interesting. Okay, so that's the initialization block. So thinking about, always sort of bear in the back of your mind these 3 things we need to do our simulation. We need our initialization, the atom coordinates and velocity. We need our potential function, and then we need our integrator, plus some bells and whistles we may put on top, like thermostats and barostats and stuff like that. Okay, so this is beginning the initialization. So then we need to create some atoms. We've told LAMMPS we're going to be using metal units. We've told that we're operating a 3-dimensional periodic space, and to expect things to come in atomic units. So now we actually need to make the atom. So we're building the initial configuration. And so what we're doing is we're specifying, because we're interested in aluminum, an FCC lattice with a lattice constant of 4 angstroms. And so we tell LAMMPS, okay, I want things to live on a lattice. It's going to be an FCC lattice, and the lattice spacing is going to be 4. Why is it angstroms? Well, if we go back a slide, we see that distances in metal units are angstroms. Okay, so we know that that's not the correct lattice spacing, but the calculation we're actually going to do is to figure out what the equilibrium lattice spacing is. And so it's our initial guess for the lattice spacing. Okay, and so things can live on other lattices, so you can look up the LAMMPS manual and you will find you can also put them on a BCC or an HCP lattice or whatever you like, and things don't actually have to live in a lattice. So if you're not simulating a crystal, but rather simulating a protein, you wouldn't use the lattice call. You would do something different. But for us, we're interested in aluminum crystal, so that's why we're making that call. Okay, then we're going to build a box. And so we need to have our fundamental simulation cell that's going to be periodically replicated in X, Y, and Z. And so we need to tell LAMMPS how big this is. So it's going to be a cuboidal block. We're going to call it box, and it's going to hold 1 lattice cell. So this is the region keyword. So we tell LAMMPS, okay, we're going to build a region. It's going to be called box. So this is our label for it. It's going to be a block, and it's going to be 1 unit in every direction, where the units are the lattice. So basically, it's going to hold 1 lattice in X, Y, and Z. Okay, and then we create it. So this is just setting up our system. So it's a little arcane the first time you see this, and you know, how am I ever going to remember any of these commands? Nobody writes an input file from scratch. You always look at another input file that someone else wrote or that you wrote previously, and you modify it. And so the basic flow is always going to be the same. So we're just building our lattice, and we're putting it in a box. Okay, and then we need to specify the lattice orientation. And so we say our lattice is FCC. It's got a lattice spacing of 4, and we're going to orient it. The X direction is going to be the 1, 0, 0, Y is going to be 0, 1, 0, and Z is going to be 0, 0, 1. And so you can orient your lattice with the crystal planes facing however you want. So this is one choice. You can rerun simulations with different lattice spacings, with different lattice orientations, and see what happens to your results. And then we need to build the atoms. So what we've done is we've told LAMP, okay, there's going to be a cuboidal region of space that's going to hold a lattice, and now you actually need to populate that lattice with atoms. So basically, you told LAMP to expect a lattice to live in this box, and now we're going to create them. So you do create underscore atoms, so that's the keyword. Every line begins with a keyword, and you can typically look up that keyword in the manual and figure out exactly what arguments it can take and what stuff it can do. So we're going to create the atoms, we're going to tag them with the label 1, and we're going to put it in the box. So the atoms of type 1 are going to live on the lattice sites we created within the box. Okay, everyone with me so far? So these keywords, don't memorize them, just look at them, understand them. They're pretty sort of intuitively named, and if you want to know more about them, look up the manual. So that's the basic message here. Okay, then we're going to do one more thing. So we're going to replicate the domain 2 by 2 by 2, and so we started with our fundamental simulation cell. So we made this thing called box that contains our lattice. And we could have run our simulation quite happily with that, because we are periodically replicated in all dimensions. And so we're simulating, or we're tricking lamps into simulating an infinite system. What we're actually doing is replicating this 2 by 2 by 2 by 2. And so we're saying, well, actually, I think maybe cooperative effects are important, so I actually need more atoms in my cell for whatever reason. So we could have just built a bigger cell from the beginning, so we could have made our box bigger, or you can just replicate this cell. And so we're going to replicate it like this. And so this is now like a supercell, and it's this guy that's going to get periodically replicated in all directions. So sometimes it can be interesting to simulate a bigger system. Typically, one of the convergence checks you might want to do for your simulation is, do my answers change as I change the size of my system? Because you want to be sure you're simulating sort of a big enough fundamental simulation cell that your answers aren't dependent on your system size. So an easy way to do that might be to add this line and write a bash script to sort of go in and change that line and make your system bigger and bigger and bigger and rerun your simulation and check your results. Very similar to what you did with your K-point sampling in Quantum Espresso. But the simulation would run fine if you just replicated 1, 1, 1 or ignored that line completely. So just a little subtlety, but it does sort of speak to a more advanced functionality that you could build a script to run on top of it. Okay, so that's, I think, all I want to talk about today. So that's 20 after. And so next week, we'll pick this up. And so if you have any questions about stuff we covered today, or if you have any questions about the project or the quiz or stuff like that, come talk to me. I'll stick around for about 10 minutes. Otherwise, make sure to deliver the stuff by tonight via Compass, 11:59 p.m., and have a good weekend.